this is our next stuff to work with. 1. Make sure you're confident with the sound interference questions before you go on to this stage. Okay, that's the first point. Next point is the Veritasium video, which I'll put a link to. There's a phase, the bit where he wanders around talking to Australian people about strange lights in a box. It's not hugely interesting, but the bit where he's in the pond and I'll come on to later, but there's a section where you really need to see where the ball's in the pond. Okay, you have all done diffraction grating practicals and they all worked, with the exception of Gabrielle, who did it via the internet. Okay, you've got to start off by understanding what D is and what the diffraction grating is. Now, the diffraction gratings we've had, okay, are basically a sheet of glass with loads of lines scratched on them, and they're kind of etched on, and there's literally thousands of parallel lines that are too small for you to see them. And each one of these functions as a barrier, so that light cannot pass through the scratch section. But in between the scratch section, you've got the original glass, and that allows light through. So we end up with the scratches being barriers, and then the gaps in the barrier, if you will, are actually untouched glass. Okay. I suppose that doesn't really matter if you can answer the questions. So, before we do the next section, let's have a quick look at our National 5 diffraction. All these gaps are going to be small enough that we can assume that we're going to get good diffraction. Now, remember from National 5 that we're representing here the top of a wave, crest, 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 and the troughs are in between. And if the gap's similar to a wavelength, you get a good stretch. Now, yeah. If you look closely at what we do, the gaps that we've got are, say, 2.5 times, they're still a good 5 times a wavelength, but all the diffraction effect that we look at is quite a long way back from the diffraction grating. So we're dealing with these kind of rays that mainly come through the middle anyway. Okay, now, this is a very interesting, important diagram, because we're looking at 2 slits in a barrier. So the blue line is our barrier. The red lines are the advancing wave fronts. And if you remember, a wave front, this is actually, the whole diagram is a wave front diagram. And wave fronts are a way of representing waves by drawing lines on the top of a crest. So we're crest, crest, crest. And obviously it's implied that halfway between each crest there will be a trough, trough, and that the crests are one wavelength apart, because that's the definition of a wavelength. Now, if I was truly gifted, I would have managed to maintain my wavelength all the way across the diagram. But unfortunately, the gifts are not that strong. Now, the important thing about this diagram is I'm just taking 2 of the gaps in the diffraction grating. And in the diffraction grating, there are literally thousands of gaps. And I'm looking at light from one gap and light from the next gap. And you can see that I've drawn in these waves coming through and they cross. Now, where a crest, my red line is a crest, where a crest meets a crest, here, 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 here. Now, if I had got more of the Leonardo da Vinci skills going, all those would have appeared on a perfect straight line, because from the middle, from here to here, is exactly the same distance as from there to there. So just using the mark on the pen, I can say from there to there is the same as there to there. So essentially, this is my path of this is my point of 0 path difference. This is going to become my central maximum. So if I go far enough away from this and put a screen, I observe a bright line, because that's my central maximum. Now, if you look closely, there are other lines where things are crossing. So from here, 1, 2, 3 wavelengths gets me to this junction, but only 1, 2 wavelengths from this gets me to this junction. So at this junction here, which maybe I should mark it in a different colour, at this junction here, I've got a crest that has gone 2 wavelengths from the bottom slit, meeting a crest that has gone 3 wavelengths from the top. And the next junction here is 4 wavelengths from the top and 3 wavelengths. So the path difference for all these green ones is actually, and you don't have to think about it for too long. If I drew another line in over here, a wavelength, I seem to be losing my semicircular symmetry, which is a bit of a worry. If I drew another one in, then I'd have another junction here, and I'm making my n equals, so where all these line up to give me my n equals 1 maximum. Now, on the Veritasium video, you see these area regions of waves, and in between them you see calm regions where you do not get constructive interference. In fact, you get destructive interference, because in between these 2 crests here, let me just find another pen. In between these 2, exactly halfway in between those 2, there must be a trough. And if this trough meets this crest here, that must be a minimum. And exactly the same thing happens here, and exactly the same thing happens here. So you can see that my minimums line up, and I end up with a line up. Here's my first minimum. And we know that for the first minimum, the path difference is, well, I covered all that in the previous video. So you can see that this diagram, which is shown in the video, is very important because it establishes how these waves, just through the principle of superposition, add up for these maxima. So I should have had that as a central maximum. And if I wanted to spend all day, I could draw circles, well, clearly better circles than these would be possible, and I could identify all the different maxima options, because of course you can very easily see there's an option here. What about this one, and this one, and this one? And that, I think that's going to be my n equals 2, my n equals 2 line. But in any case, this explains what you see in the video. You see a region of waves down the middle, then you see a kind of region with no waves where you've actually got destructive interference, and then you see a region of strong waves again, and then you should see a region, another minimum where there's a region of no waves, and then another maximum. And that's clean to see on the video with the Australian chap. Now, this looking at 2 waves, 2 gaps in the barrier, is a simplification of where we end up. So the same diagram now would have hundreds of these lined up, and obviously that's beyond the limit of my circle drawing, and but the result of this is that all the different gaps in the diffraction grating contribute to the addition. They contribute to this building up, and building up a series of lines. And so they actually tighten up the pattern so that we end up with very clear, bright points on the screen. Okay, so I just wanted to kind of do a bit of a link. So yeah, it is like this, but this would only be a small section of that, and this would be an enormous version of the original, of the previous diagram. Okay, let's get on to talking about how we solve problems. Now, in the questions, okay, let's just talk about how we measure different things in the system. Now, here's our diffraction grating. And I've decided to illuminate it with a laser beam, which is a very convenient way. Now, having done that, you can see that I then get on a screen that I've placed over here in my 3D diagram, I've got light that continues straight through, forms my central maximum. Well, light that has 0 path difference when the different contributions from the different slits are added together. Then I've got my n equals 1 point, n equals 2, and if you remember, these are bright points on the screen, And you don't see these lines unless maybe you sprayed it with an aerosol or something to show up the path of the laser through the air. So you're just going to see bright spots on the screen. And we've got central maximum, n equals 1, n equals 2, n equals 1. You've got to remember this because we're going to need the n in the equation. So the theta is always measured from the central maximum. So that's a very important rule, that you measure your theta from the central maximum, and you might be given the angle to the n equals 1 line. You might be given the angle to the n equals 2 line. That might be your theta 2 or whatever. You might be given the angle all the way across, which is actually be, say, n equals 2, 2 lots of the n equals 2 angle. So you've got to think about your angle, but in any case, it's always measured from the central maximum. So we've talked about n, talked about theta. Now, if you were doing an experiment or you're asked to construct an experiment, the most efficient way to measure this angle, or the way with the least experimental uncertainty, is to measure the biggest angle you can. So in this situation, I would measure, if I could, the angle from the n equals 2 line there, all the way to the n equals 2 line over here. So I'd measure this really big angle, and when I'd measured the really biggest angle I could, I would then divide by 2 and know that that was the angle for n equals 2. So I might measure 2 lots of it all the way from over here to there. Once I've measured that angle, I would say, okay, the theta in this question is going to be half of this big angle if I substitute 2 in for n. The only other thing you could be asked in a question is they could force you to do a bit of trigonometry first and give you a length here, give you this length, and give you the distance between the diffraction grating and the screen like this, and say, okay, we'll essentially give you, and you can do some trigonometry to work out your angle. You might have to do a tan first to get the angle, and then once you've got your theta, work onto something else. Okay, let's move on to an example. Now, people often misuse what they're told in the question. You're told how many lines per millimeter are on the diffraction grating. This number is not really much use to us because remember our equation is n lambda equals d sine theta. So the number of lines on the grating, lines per millimeter, is not d. We have to calculate d unless we have a very generous question that gives us the distance between slits in the grating. So we have to get the distance between 2 consecutive lines, slits, gaps in the grating, d. So let's take an example. If I've got 50 lines per millimeter, the methodology for this is to go from lines per millimeter, multiply up to get lines per meter. So that's easy enough. Millimeters to meters times by 1,000. So 50 lines per millimeter, 50 times by 1,000, 50,000 lines per millimeter. Then you want meters per line, not lines per meter. So you just take the reciprocal. So I do 1 over 50,000, and that gives me my distance between my lines of 2 times 10 to the minus 5. Now, this is always going to be a small number. So it's always going to be sort of 10 to the minus 5, 10 to the minus 4, or your diffraction berating probably won't work with visible light. Right, so let's do a complete question from start to finish, and then we can finish. So I've made up a question, and I've said, find the wavelength of an unknown laser, and I've got the grating has 400 lines per millimeter, and the first maximum occurs 12.5 degrees from the central maximum. So, it's easy enough. I've started off doing exactly what I've just said. So for D, I'm doing 400 lines per millimeter equals 400,000 lines, lines per meter. D of 1 over 400,000, which is 2.5 times 10 to the minus 6. Okay, so now, looking at the question, I've been given very kindly that I'm on the first maximum, so I know that n equals 1. I know we wouldn't normally bother writing in 1. So lambda equals, now I've got my D, 2.5 times 10 to the minus 6. And I need to multiply that by the sine of 12.5 degrees. And that would appear to be my problem sorted out. So as I don't have a calculator, I think I'll stop there and leave you to work that one out for yourselves. Okay, that's the methodology. You can do that one and then soldier on through the course questions on diffraction gratings.